Good afternoon again. So the last speaker today is Yang Liu, who will speak about curvature and non-commutative probability. Please.
Good afternoon, everybody. So this is going to be the last talk of the day. First of all, I would like to thank you all and the other organizers. It's a kind of a surprise opportunity here, but it's always a great pleasure and great honor to be able to speak in a conference. So yes, today, so my topic will be about, so this week, I think one of the main topics is about non-commutative topology. So here, probably my theme here is about non-commutative differential geometry. So, and I would also like to sort of put the two topics that covered in yesterday and this morning, but not yesterday, Tuesday, I think, by Anna. So this is a Truman triple and a quantum Levi process, and this modular theory. So talk about this for phenomenon algebras. So put in the context to differential geometry. So, and the sort of the main question. So the general question behind is to sort of explore the notion of a curvature, especially the notion of an intrinsic curvature in the Riemannian geometry. So in the framework of non-commutative geometry, in particular, using this language of using the language of operators on Hilbert space. So okay, so first of all, so So we know that once you have a space, right? So you take a dual picture, you consider functions on space. So in our context, we use like continuous functions. That's so-called the Gelfand-Neumann duality. So you get from geometry to some algebraic structure, and then in algebraic geometry. So we also use this dual picture, but in algebraic geometry, they consider like polynomial functions. So when the next step is to bring in the notion of to do geometry, we need a notion of a metric in here. I think sort of one of the signature feature in NCG, in the sense of Alan is to how to bring in the notion of a Riemannian matrix into an algebraic context. I think this is quite a sort of a non-trivial observation. So here this is these are the general templates of a non-commutative geometric space. So it's motivated by this Kahn's model for spin geometry. So of course we dualize this the geometric space to its functions. In here, since we are doing differential geometry, we consider smooth functions. Well, so the metric here is represented by the so-called Dirac operator. So here the spin geometry, the spin is kind of a topological conditions like an orientation on manifolds. So which is required to define this Dirac operator. So I think this sort of yes, I mean so this idea of using Dirac operator to bring in the Riemannian metric is somehow, I think it's a deep observation that if you read Kahn's survey paper like this, I think this will never come. So if without the development of this quantum mechanics and the development of this, so the Atiyah single index theory is two huge achievements in the 20th century that motivates him to use this Dirac operator to implement a Riemannian metric. So so now the general, so the general space, so it's a they call it spectral triple. So this A can play the role of the algebra of smooth coordinate functions, while D is the sort of Dirac type operator, and they interact on some Hilbert space H. So here we need a star representation, which represents A as a bounded operators, on this Hilbert space, and then this D is an unbounded self-adjoint operator. So the basic requirement is that you have this for any like a so-called like smooth functions, the commutator is a bounded operator. So I mean, this is the basic requirement. Well, so if we look at this example, there are much more, like a long list of axioms that sometimes one would like to put on this triple. So, but from my point of view, is that once we have such a triple, so important or like interesting tool is to consider this so-called special zeta function here. So actually, so once you have some good enough tools or axioms to study or like to prove that, to establish this existence and analytic continuations of such a special zeta function, I think then we're in a good point to develop a lot of interesting quantities. So basically, so I'm interested in the sort of in study this the so-called special values of these zeta functions. So in the context of the Riemannian geometry, this will recover the notion of curvature, like, and other geometric invariants. So I will explain how. So without further ado, let me dig into an example, since like not everybody's in the background of differential geometry, but I think everybody likes torus. It's just calculus, doesn't require much of a deep knowledge of differential geometry. So let's continue. So I will use this quantum two torus as an example, which this is the simplest but the most resourceful examples in non-commutative geometry. So on the left column in here, it's the classical notion of functions on torus. This generators, this u and v, this x, say if we put x and y, they are the coordinates of these two torus. So and uv is the e to the ix, e to the iy, and then all these for smooth functions, we can expand them into Fourier series in this form, right? And then smoothness is characterized by this rapidly decayed of this coefficient. So, and then we have partial derivatives here. So okay, so all these notations translate basically verbatim into the non-commutative case. In I think the only difference is here. So we have this these non-commutative relations of this u and v. Well, otherwise, I mean these notations basically they are the same. You can pretend that you are working with the functions on a torus, but with a deformed multiplication in this. So okay, so these are the basic. This is the differential structure, like this way. So so when doing calculus, so you need also integration. This basically the Lebesgue measure. Usually Lebesgue measure is basically, I would denote this by this phi zero. It's the same. It's the same thing here. Phi zero. So if we represent some elements on this smooth non-commutative tutorial, so and then this integration phi zero function. So this function only takes the constant Fourier coefficients. And with this, this is a trace. So and then with this, so we can use the classical like GNS constructions to define a inner product, and then we complete to get the Hilbert space. This Hilbert space is basically playing the role of these L2 functions. So any questions so far? Okay, so now we have a integration, differentiation, and integration. So for spectral triple, so this Hilbert space H usually consists of two parts. So here, which is a direct sum. So here is the H0 will be the functions, start with like a L2 functions of this space. And then probably the next components will be the L2 sections of, say, differential forms or some other similar structures bundles. So what's the next piece in here? So then the next piece, so here, basically we're gonna upgrade a lot of the result on Riemann surface in this context. So then there is a sort of a complex structures here. So the second part of the Hilbert space is the analog of these 0-1 forms. So we want to put a sort of an inner product on it. How to define this? So let's consider the classical torus. So we know that there's a 1-to-1 correspondence between the conformal structures of this and the complex structure, and the complex, and that they are both. So it is parameterized by some by complex numbers on the upper half plane, and up to the actions of the modular group. So here is the parameters for the conformal or the complex structure. So and then with this, so we can cook up the analog of this Cauchy-Riemann operator. So this is and then to form the 0-1 forms. So first of all, so we take the underlying algebraic space is we take, say, finite combinations of elements of this form. So this should be like at this level it's just say elements in A tensor A. Right. But here, so these two parts are sort of some difference, because you have this differential forms like A, D, B, right? So that's why I put in this form. It's a finite sum of this form, and then I think for the Hilbert space, the only crucial thing is the inner product. Here is requires some deep observation in here. So the inner product used by Kohn and Moscovici in their paper is the following. It's the following form. So it is here. So the ingredients is a sort of a multilinear functional. If you don't know whatever this Hochschild-2 cocycle is, it's a multilinear functional on this algebra. It has 3 inputs, and then here it is. So the analog on the Riemann surface is, so this functional, this positive Hochschild-2 cocycle is uniquely associated with the underlying complex structure or underlying like a conformal structure. Yes.
Sorry, I'm probably missing something, but this partial derivative, is this somehow formally defined by this?
This is just a symbol.
Okay.
This is just a symbole.
Because the deltas are down there, and somehow they are involved in psi, and psi tells you the scalar product between such formal elements.
Yes. This is a symbol, and then it will be a map. Like in a minute, it will be mapped in a minute. So okay, so basically this inner product is sort of is independent of the conformal change of matrix. So it's depends by it's grasped by the underlying conformal structure. So by the way, there's also sort of a idea of Kohn is to grasp like a complex geometry, like in this approach. So in this so if you view this so for example, let's in this example of a noncommutative tutor, you can view this Cauchy-Riemann operator as a sort of a complex structure, right? So but well, if you want to go beyond, this is two nice examples. If you want to go beyond, you can use a sort of a linear function. These are linear functionals like that. So this the complex sort of the complex structure introduce some positivity. Let's look at this example. So okay, so the classical counterpart is the following. So in here, so this functional, so if we use this the usual exterior derivative, this functional is not positive. So oh, by the way, the positive, well, it's the of a multilinear functional. It's due to Kohn and Kunz, sort of generalize the positivity for bilinear form. So but anyhow, so using this complex structure, right? Once you have a star A, so you have some positivity. So that's where this positivity comes in. So this is this Hochschild cocycle is in the same class of the fundamental class. So it's like Korn's idea is like to define this complex structure. First of all, so the complex structure becomes some positivity, and then inside this this positive element intersects this co-cycle. Co-cycle is a class. Consider a sort of a collection of a multilinear function. So if you impose the positivity, then you are in a positive cone, and then you search for some optimization problems. That's where his idea to approach complex structures. But this doesn't go beyond like dimension 2, because on Riemann surface we know this correspondence between conformal and complex structure. But anyhow, that's his idea in this book, in his books, to approach like a complex geometry in this functional analytic setting. So. Okay, so here is the analog of this. You can see that so here is here is the Lennon's positive currents. So, and then you can rewrite it in this way using the standard volume form. So here is the corresponds to phi0. So this is the standard volume form, right? So and then these are the Cauchy-Riemann operator and its adjoint becomes the delta and the delta star. So that's how this analogy goes, like from the Riemann surface to quantum. Any questions? Okay, so I will just erase this. So with this inner product, then comes into this operator in this operator here. So now I view this as symbol as an operator sending A to delta of A, right? So it's a now it's first of all you define like usual differential operator. So first of all you define on the natural domain. In this case I choose smooth functions, and then you extend to the L2 function. So then from here, basically they are the same. This little d is the close extension of this positive. So yes, I think the crucial ingredient here is the inner product. Once you cook up an inner product, so that's then we are safe. So then we're almost here. So now the conclusion is that we have a spectral triple which sort of carries this flat Euclidean metric. Okay, so now if you're doing this flat metric, you don't get anything new, right? So because this D, the spectrum of D is basically the same as whatever happened in a classical case. So okay, so now let's to make the game more interesting. So we're gonna introduce a class of curved metric. So we consider basically on Riemann surface. So because we already list all these conformal structures by tau, right? So the next step is to consider all the conformal change of the metric. So if you believe this this analogy of this okay, I will not dive into that direction. So okay, so we want to do some conformal geometry. So we want to implement some conformal change of metrics. So how to do that? So in this framework, so first of all, we just change so once you do this conformal change of metrics, so this volume form, this integration get changed. So here appears we're gonna rescale this the Lebesgue measure by a conformal factor e to the h, where h is a self-adjoint element, so that e to the h is positive defined. So and then we can still do this GNS constructions. We have a new Hilbert space. So yes, the point is to change the inner product. So okay, so now here, so this so after this change, unlike the commutative case, this new phi is no longer a trace. It's a twisted trace. It has the K-S property. So like this. So this leads to this modular theory. So this So this conjugation sort of by e to the h going to generate this the modular group, which measures the failing of being the phi being a trace. So and now it comes to another interesting point of view. So about this non-commutative work. So okay, so now after changing this rescaling this volume, so now for this spectral triple, so the representations you can use left multiplication and a right multiplication. So in this flat case, it doesn't give you much difference. However, so once you change your inner product in here, so this right action, right multiplication is no longer a star representation because of this barrier of this. So then you have to modify this modify this right action by this Tomita antilinear. So okay, so now in the non-commutative case, so this left representation, right representation gives you different geometry. So if you are in a if you still consider left representation, you will still have a spectral triple. However, if you consider right multiplication, so we modified the right action in the following way using this Tomita antilinear unitary operator, and then it's so the here is not the commutator is bounded. This twisted commutator is bounded. So basically here you have two choices. One is left representation. The other is right representation. Right seems to be bad. It's not a spectral triple. It's twisted spectral triple. But when you're doing this geometry, so you're going to challenge yourself. I'm not going to do this easier thing. I will pick the right representation, this harder one, and then I will study this. Twisted spectral triple. So now and then okay. So the geometric part ends here. So from here. So because we're working with Hilbert space, we can always cook up some unitary equivalence between these two Hilbert space. And then basically I want to change everything onto this Hilbert space. And eventually this Laplacian operator, which is it looks like this. So basically I'm going to extract geometric local invariance from the z function of this Laplacian. So any questions so far? So let me just erase this. Okay, so before going on, so I need somehow to review some basic results in Riemannian geometry. So our this approach of curvature is modeled on the spectral geometry on Riemannian manifolds. So how to get this? How to get to this? So for example, how to recover this scalar curvature? So if you look at this, you take a geometric operator like a Laplacian type. So it could be like in a classical setting, it could be like squared Dirac operator or the Laplacian operator, and then you study this small time asymptotic expansions of this heat trace. Viewing it, so here, we view this as a linear functional in F. So and then all these coefficients gonna encode a local invariance. So I index this J in such a way that this J is equal to J here is equal to 0 to this even numbers. So when the manifold is closed, so all the coefficients they are 0. So for example, so for J0, it's constant function 1 up to some universal constants. And the second coefficients, it's 1/6 times the scalar curvature, where this operator is the scalar Laplacian operator. So this allows you a way to use use the pure like a spectrum framework using linear functionals and to recover this scalar curvature. So and then this heat trace, and then there are and these zeta functions, they are sort of the twin brothers by this Mellin transform. So if you, for example, if you know if you can prove this heat as this small time asymptotics for the heat trace part, and then you equivalently you can, using this the standard Mellin transform arguments, you can establish these analytic continuations of the zeta function. They have the poles and sort of the corresponding coefficients will determine all the poles like accordingly. So any questions? Okay. So in dimension 2, this second coefficient corresponds to the zeta function at 0. So okay, for example, so if we want to use the zeta function here, so the first result on this direction is so-called the Gauss-Bonnet theorem. So on non-commutative, so first proved by Kohn and Trekov. So and later, so Karkali and Fatizat, so they sort of finish some so this contract of this computation for the complex structure tau is equal to I. So and then this later they did this for the general complex structure. So but the point here is to, so basically this zeta function at 0 recovers this integration of the scalar curvature on the Riemann surface. So here the theorem using this zeta function formulation is to show that for any metric, right? So the H represent a metric. So here, so now we have sort of consider this conformal class of metric. So parameterized by all these conformal factors e to the H. So then the H sort of the self-adjoint part is sort of can be viewed as the tangent space of your metric. Now this is an infinite dimensional space. So parameterized by all these self-adjoint elements in here. So now I defined a function. You can view this as a function on this class of metric. Then this class of metrics. Now the Gauss-Bonnet theorem says that this is a constant function in H. It's like means that the integration against the scalar curvature is a constant. Then in a setting of Riemann surface, this is the Euler class, the basic class. So okay, so now
sorry,
yeah.
I have a question.
Yeah.
Usually people thinking about these conformal classes,
yeah,
they consider them up to diffeomorphism of a classical space.
mm-hmm.
And then this space of isomorphic classes of these conformal structures
Mm-hmm.
is finite dimensional. It's a moduli space.
Mm-hmm. Mm-hmm. Here,
Okay.
I think here I just consider a functions on this non-modular diffeomorphism.
Okay.
Yeah, non-modular diffeomorphism.
Okay.
Well, I mean in this quantized we don't even know what is the diffeomorphism on.
But you have this smooth structure.
Well, but I don't.
Can't define this. You have a smooth algebra.
Yeah, and then how to
So-
define diffeomorphism?
Automorphism.
Well, well, I guess there's some tricky part, but we can discuss later. So this is so here, but yeah, the point is I do not modulate this actions of diffeomorphism.
And Lycon studied some spaces of his quantum theory.
Okay, so basically this zeta function at 0 doesn't sort of now you integrate, it's a constant function, you don't get much. The next step is to study this part to get an interesting functional. So then this is known as Ray-Singer determinant. So of this Laplacian. So basically, so this the paper on Oscar Philip Sarnak. So they consider this array single determinant on Riemann surface. I think this is so this, and then they use this functional so somehow to prove the uniformization theorem. On the other hand, so this by slightly modify this array single determinant by integration of this. So and then so when doing this variation, so in the following sense, when doing this variation, so and then it recovers the Hamilton-Ritchie flow. So that's why that's basically the idea of Kohn and Morse curvature to approach this this modular Gaussian curvature. To use sort of some variational arguments. It's like for example, like on manifolds, so say when dimension is higher than 2, I think it's if you variate the Einstein-Hilbert action, which is the integration of the scalar curvature among a conformal class, and then you're going to recover the scalar curvature, right? And then if you're doing this variation for all among all the metrics, then the corresponding equation is the famous Einstein equation, and then that's the way you sort of encode the Ritchie curvature. So that's basically I think this sort of a approach that Kohn and Morse curvature want to use in this setting. So here, so what's the
sorry, I have a question. Is your phi 0 normalized to 1?
Yes.
Okay.
Yes. So okay, so here is the variational language, like in this operator theoretical setting. So it's so because we are defining a function of on all the self-adjoint elements, right? And then I can consider the directional derivative. So I can add doing a perturbation along some other self-adjoint direction, and then you compute a derivative. So and we know that this derivative is always a linear functional in A, right? And then we can further doing some hard calculus to compute that this linear functional in A can be represented using phi 0 with the functional density. So this is we call it the gradient, the derivative. So
Young,
yeah,
it's Ludwig. Hi.
Hi,
Can
Ludwig.
I ask you? Hi.
Yeah.
Can I ask you? So in general, if H and A do not commute, this H plus epsilon A may be not self-adjoint. How you overcome this? You don't. It doesn't matter.
Doesn't matter.
Okay.
Which part is not self-adjoint?
H is positive self-adjoint. A is self-adjoint, but H plus epsilon A may be not self-adjoint.
Why? Why? I think
If epsilon is positive.
yeah, epsilon is a positive number.
Well, doesn't. I mean, if they do not commute, it's not always sum of two.
No, it's a sum. It's not product. It's self-adjoint, right? So it's
also then it's not always perturbation of self-adjoint by self-adjoint to self-adjoint. Not always.
right. So it's a right.
But H is bounded in your case.
Yeah. A is a bounded. A is an element.
Okay, and A is also bounded.
So A is bounded.
Okay, maybe in that case. Okay.
A is bounded. Okay, so now. So okay, so what's the okay? So the next slide. So I mean, originally I don't want to put all these formulas in this talk because it's very late, right? Everybody's hungry. So, but okay, so I want to explain what sort of some conceptual ideas behind all these formulas. It goes like this. First of all, I mean, the essential difference, so compared to the classical case, is the following issue. So the derivative, this H, these coordinates of the metric, which is only one element, do not commute with the derivatives of H. Right? There's no guarantee that when you differentiate, it will commute. So that's the fundamental difficulty when you're doing calculus, and then you have to use set up a whole set of a calculus to do this. So that's sort of the difficulty from calculus point of view. It's like a differential. So here we are trying to extract invariance out of smooth structures using differentiation. Now it's like the coordinates you start with do not commute with their derivatives. So that gives you a sort of a completely new ingredients of this curvature, of all this local invariance. So and then when doing calculus, then we can use either this commutator or this conjugation sort of to switch order, right? To rearrange elements. So I mean these operations. So happens to be the sort of the modular operator or the modular derivation. They are the generators of this modular one parameter group of modular automorphisms with respect to this non-trivial weight. So that's why this is we call it modular. So basically we have to collect fight hard to collect all these actions of the modular operator or the modular derivation. They are basically up to a change of variable. Right? So here is the classical part. The derivative of H now comes from the modular part, consists of now everything can be grasped by these two functions. In here, what I'm writing here is like you can think of K and H, they are power series in some X or in some X1 and X2. Okay. So when you replace this, so not or even polynomial, right? So then you replace this X by this modular derivation. Well, and this 1 and 2 means that I put this modular derivation on the first or on the second factor. So this the point is that you're going to compute a lot of you can capture all these actions by two functions K and H. So I mean this so for example, like we talk about a lot of Q deformations, right? So when you compute interesting quantities of this Q deformations, somehow you're gonna encounter special functions, a lot of special functions in Q, like modular forms, a lot of special interesting functions in Q. So here you have the same phenomenon. So when you're fighting with non-commutativity, so you are encounter some interesting functions that carries out this rearrangement process. So and the first observation of Cohn-Morse curvature is to show that this is an intriguing function. It's the generating function of the Bernoulli numbers. So and then the second interesting observation is to show that there is a simple functional relations between K and H. This is going to reflect the fact that this curvature in here, so if you set this equal to 0, this is basically this Euler-Lagrangian equation, right, for this variational problem. So being a Euler-Lagrangian equation, so we naturally expect these two coefficients have some relations. So there is a simple relation. There's a simple relation. So this is yes, I think I devoted a lot of time to really understand this sort of these new ingredients, and then. So I think one new observations I show that these functions, they are related to some hypergeometric functions. After all, they are like interesting functions. The other side is if you look at these three terms, you can see two structures. The one is the sort of this divided difference structures, these three terms. And the second one is a cyclic structure, which if you look at how this S1 and S2 changes in these three terms, there is a cyclic permutation of order 3, like behind this. So there is I mean, I think this cyclic actions is sort of related to this cyclic group in the theory of cyclic homology or cohomology. So okay, so this.
Sorry, I have a question. Is there some complex in which this H is a co-boundary of this K?
Yes, that's
It
a
looks
part
like-
of something I'm working. I want to achieve that. Yes, that I want to achieve. So that's I'm probably like 60% or to get that. So that's yeah, exactly. So okay. So and then I mean, think so the starting point I get involved in this project is to extend this all this discussion to a larger class of examples. Like the next example I did is they call this Cohen-Landy deformation, or like a toric non-commutative manifolds. So basically you can deform so you pick your favorite like manifolds, like spheres, like torus. Once it has a torus action, so you can deform deform everything like so for example, we can deform this algebra by these torus actions. So then for the Dirac operator, we need a sort of so G and Tn invariant metric. Yeah. You mean refer, right? So refer, yes. I think probably like for the spectral triple, I think it's a little bit probably at the same time, and you see that. So refer developed the whole this analytic aspect of this data deformation. But I think Cohen-Landy's paper, I think they write down this spectral triple. I mean, probably it's a little bit earlier. Thanks for that. Yes. So now so basically the conformal change of metric, so reduced to sort of to change this perturbation of Dirac operator. This is also from spin geometry. There is a formula, so we just take that from that. And then you can study you can compute it, say, for example, the second coefficient in there. So we're gonna get a very similar result as I just mentioned before. So in this way so we have enough examples from all dimensions, not just dimension 2. And another features is that so in this formalism, so I can still carry out. So because in that setting, so I can still carry out. There is a scalar curvature of G, which is the background metric of D. So in the torus case, the background metric is flat, so you don't have any curvature. But if, for example, like if you take something like sphere or something like, then this D already carries some scalar curvature. So in this case, I can show that the background metric from D and this new quantum part, they merged together in a perfect way. And then for example, like if you take this formula, you take the deformation parameter to 0, then you will recover whatever the classical result. So okay, here is just the very brief review about this modular curvature stuff. So now I will completely switch gear. So the question for me is that so then the question is, what's the next class of sort of non-commutative manifolds that I can try to do such computation? Well, on the other hand, it's so even though we have very good analogy, right? So compared to the case of Riemann surface, but you see that this curvature, the classical curvature will tell you the shape of the manifold. Like the curvature will be some obstruction of some topological property, right? So I mean, in this case, it's very hard to say like what does this curvature mean, right? So we have this analogy, we compute something, right? So then I think this once we come to this non-commutative probability side, I think we can. It's a right place to look for the meaning of the curvature, because I think this is phrased somehow already in this functional analytic setting. Because in the classical case, like this shape and whatever this obstruction, probably it's because like a non-commutative doesn't have shape. I mean, it's right. So once you give up this geometric picture, so And the third point is that I'm looking for more examples where this modular theory. So it's like you have the volume functional is non-trivial. Then it now when in this case it attached a sort of a natural like a dynamical system, right? The action of this modular group. I want to find more examples with this phenomenon, like, and to see how this action of this modular group like get involved in this notion of curvature. So I guess this quantum SU2Q, so that the spectral triple I will present. So it's a construction in the paper. So I was just doing some digging, and then this construction I found is paper by Cipriani, Franz, and Vysotranska and Kula. So I pray yes. Yeah, you all told me how to pronounce it. So okay, so in the next 15 minutes, I will describe a construction of a spectral triple from this non-commutative probability side, and then I think you will see that it's very similar to the constructions I presented at the beginning. So okay, so before I going forward, let me just if you don't like curvature, just forget about curvature. Let me just review what's the construction of this spectral triple at the beginning. So basically you start with some Hilbert space H, right? This is just the L2 functions of your space, EZ, this part EZ. The next part is you want something like a differential forms. In here, like Cohn-Morse curvature use this 0-1 form, like we call it holomorphic or anti-holomorphic, I don't know. So and then I think the sort of the juicy part is how to find a sort of a deep inner product in here. I think this this Kahn's Hausdorff glucose cycle here. So now you find some Hilbert space. I mean the difficulty is to find a nice way to define this inner product, right? So, and then by the way, the inner product tells you what does this mean. I mean at here is just a symbol like a D form of symbol. But once you have this inner product, you can really and then it enforces that this D will play in the role of this complex differential. Okay. Okay. And then with this, then you define this operator. First of all, you define this on some smooth elements, and then you extend to the level of L2 space. So that's basically the procedure I'm going to go in the next example, which is from the non-commutative probability side. So, okay, so now the next example, we look at the compact quantum group. So this I'll use so this I will consider a sort of a substar Hofstar subalgebra inside. I mean, probably in this case, I will take for example, like polynomial algebra. So I will not consider the C-star version. So by the way, so I was trying, when I prepared the talk, I was trying to explain what is compact quantum group, but then I think I'm in the Bata Center to give a talk in Poland, so probably there's no need to explain what's the meaning of a compact quantum group, so I guess. So, and there are many talks about this compact quantum groups. I think the most, I think for me, the most important part is that why we want to use quantum groups. Once you have a co-product, using the co-product, you can turn any linear functional into a linear operator by this convolution. You can use the L stands for left, right? You can do this left convolution or right convolution, right? To turn any linear functional into a linear operator. I mean, in this case, so in short, in this way, like the Laplacian operator will comes from some convolution operator, some linear function. That's so that's the rough story. So it's like I'm going later there will be a Laplacian operator, this LP, so which playing the role of Laplacian operator. So okay, so once you have so you can keep this as an example of this SU2Q, I think. Okay. So there is a hard measure. Once you have a hard measure, then it's so you have the GNS representation, right? H0, that part is easy. So now the comes from the one form part. It's now this one form part is replaced by this so-called Sherman triple. So I think Anna gave an excellent talk on Sherman triple, so this I'm so glad he did all the heavy lifting. So I'm just maybe in the next 2 slides I will basically review some basic definition and then probably contributes one small observation. That's all. So okay, so to define the spectral, a spectral triple, so basically I have to explain what it basically about this, what's this Sherman triple. So okay, so as before, our in this spectral triple, so the Hilbert space consists of a direct sum of 2 parts. So this part is the functions. This part is well, I'm not going to call it differential forms, but that's the vague analogy in here. So this H1 comes from this data H1 comes from basically the Sherman triple. I think this so I should write it H1 is equal to H0 tensor some H pi. So H pi is the Hilbert space in the Sherman triple. I will explain in a minute. So and then here's the representation of A acting on H. So this is this is in H1. So this is the B is in H0, B is in H pi here. So the left representations I use lambda L is just the left multiplication. Well, and then pi is the representation in the Sherman triple. Here the action involves some co-product. So that's the formula. So and then after I review the construction of the Sherman triple, then I will finish the construction of D. So basically that will conclude my talk. That once I explain what is this little d, basically I will conclude. That's the end, basically the end of my talk. But so any questions? Yeah,
because you introduced what? So H1 is a tensor product of H0 with H pi.
Yeah, H pi.
So H0 is somehow twice there.
Yeah.
Okay.
Yeah.
Okay. Now I see it. I see.
Yeah.
Okay.
Well, you see that because like one form you can it looks like A tensor A, right? So this like differential one form, right? It is like so this part plays like functions, this part plays like forms, right? That's why you have this tensor.
I have a stupid question. I don't understand your pi L. So the domain is what? A, and you have a tensor product?
Thank you.
Okay,
Oh, this
fine,
is-
but then
this
how
is-
do you act with a tensor product?
Oh, this is direct sum, I guess. So this will act on H0. This is a direct sum. Thank you. This is a direct sum. I will.
Yeah.
So when acting on functions, you just
Yeah.
do left
Yeah,
multiplication.
I'm happy, yes.
Yeah. On this H1 part, you're gonna use a rho L. This rho L is defining. Yeah. Okay. So okay, so here, now, given a sort of a star pi algebra, so these co-product co-unit, so you can define a Sherman triple in the following way. So now you want the pi is a star representation on some pre-Hilbert space E. So here I'm using the notation L of curly L of E to denote the set of linear operators with well-defined adjoint. So that this is a star algebra. So the next ingredients is they call this pi epsilon 1 cocycle. So which is a linear map from A to this pre-Hilbert space E, and then this is the condition in here. And the next part is so we require that this is sort of a, once you have the eta, then you have this bilinear form. So we want this bilinear form to be a 2 co-boundary or from phi here. So phi is a linear functional. So here is the condition in here. So okay, so basically, so yes, so I will give my interpretation of why we put this action. Okay, first of all, let's how to motivate this. So how do I look like these two co-boundary conditions? Because eventually this because we have co-products, everything. So from co-products, the linear functionals can becomes like linear operators, right? So then we look at what happens for linear operators. For example, like if you have a Laplacian operator, right? Formally, it can be written like this, minus now squared, right? So, and I mean, in differential geometry, we can often play this game. So this is when if you teach Riemannian geometry, so probably this formula then it appears once, right? So when you teach some course in Riemannian geometry. So this is the Dirichlet form for the Laplacian operator. So and then what's behind my point is that once you have some abstracts like second order differential operator, right? How do you recover the first order one? Then you can use this formula. So in the context of this Markov diffusion theory, they call this a Carry-Duchamp operator. This is so using this, right? So so you can really recover this sort of this first order part in this way. So and then this is, if you look at this formula looks exactly like this part. Like phi, if you think phi this L phi is just the Laplacian something, then this looks exactly like this. So this formula looks exactly like these two co-boundary conditions. So okay, so this is my like personal way how to memorize. For example, if I want to memorize this formula, I will go to this formula for the Laplacian. Okay, so I mean basically this definition, this is a sort of a cohomological reformulation of this so-called Hermitian and a conditionally positive linear function. So basically, so the definition is the following. Hermitian is easy to understand. If you put star, then you put the conjugate. Well, and then the conditional positive means that it is positive on this kernel, on the kernel of the co-unit. So the question is how to classify all these conditional positive linear functionals. So the data of this Schurman triple will give you a sort of a cohomological interpretation, like the positivity traded to the existence of such eta. So okay, so for example, like given you a positive linear functional, how to recover a Schurman triple, so then you sort of you define a sort of a positive equilinear form in this way, using this conditionally positive linear function in this way, and then you basically you're going to mimic the GNS representation. So because of this positive linear form has a null space, you just modulo this null space. That's your pre-Hilbert space. Now you define that this eta will be just the quotient, standard quotient map, right? And then you're gonna check. So then you can check that all these axioms, or then you can check all these axioms in the posted here. They're going to be fulfilled. Okay. So now I'm perfect timing. So okay. So now let's to conclude the construction. I'm just have to tell you how to construct this differential, this Dirac operator, this D star in here, right? So in here, so it's basically so we're defining, so similar to before, we're going to defining a map from functions to this sort of a one form part. How to do that? So we use eta and plus the co-product. So that's the formula. So and then you defined it on this a star subalgebra, and then you extend to the L2 level, and then you can, this is called D. D is the extension of delta. And then you put D adjoint, then you sort of get a spectral triple this way. And then you can check, this is the derivation property. So this D satisfy this derivation property. Well, to check this derivation property, so we need a bi-module structures of H1. So I explained the left action at the beginning. The right action is it's easier. It's just we use the identity for this. So in here, so basically, so we have a sort of a construction of the spectral triples. So in this way. But yes, I mean this. So yeah, I mean so basically it shows that potentially there is a starting point to ask all these questions I mentioned for the non-quantum tool. I mean potentially to move on to this example. Right? So it's and also this example has this if I'm just talking about this quantum SU to Q. So it has a non-trivial Hahn measure like this. So I was, yes, really want to find something. If it would be great to find some sort of a local invariance like curvature, which involves this the underlying modular group, like in the previous case. But okay, so here's the end of my talk. So here is the reference of the Anna's paper, and this is the paper of Kohn and Moscovici, where they developed this modular Gaussian curvature. Thank you.
Comments, questions?
So I'm not an expert in these geometric things, but I remember that when we construct these algebraic differential forms on quantum groups, then at least, well, it is important to check if they are covariant under the action of the group on itself.
Mm-hmm.
And if they are, then in most cases they are classified. So it would be, well, nice to know if that construction of these differential forms that you performed, if it fits into any of those known schemes or not. I mean,
yeah,
is it
indeed.
covariant under,
Yeah.
does delta act also on the differential forms? That's
Well,
the question.
This part probably
Okay.
Well, probably even if it's not, probably it's
They
not
are
big
sometimes covariant only on one. Yes, but sometimes the requirement of covariance implies finite dimension. Yeah. Okay. All right. Thanks. Oh, by the way, okay, and it's for Ludwig. If at least one of two self-adjoint operators is bounded, then the sum is self-adjoint.
Yes, of course. I just forgot that H is bounded.
Sure.
Yes. Yes, I think here it's probably like we don't need to use differential forms, right? This spectral triple construction is quite flexible. I mean, in this case, I think this sort of there is underlying this because the Schromann triple when corresponds to some quantum Levi this process by solving a stochastic differential equation. But what's behind is sort of a diffusion process, like quantum diffusion process. There's some dynamic system which somehow like impose some Riemannian geometry. I mean, in a classical case, like this heat flow, right? So somehow corresponded to the underlying Riemannian geometry. I guess that's the picture for me from here.
Young, I have maybe it is in the paper. I couldn't find. Did you say about the compact resolvent of this?
Oh yes, I think they proved that this D has a compact resolvent. Discrete eigenvalues.
Okay, thanks.
Yeah. Yes, I think even one more elementary question is that if you, it seems that nobody has followed in this this direction. It's like, for example, the first question should ask is that if this construction provides new examples of the known spectral triples on SU2Q, but because of the classically they are constructed in the spirit of like this spin geometry, like the spinor bundles. Yes.
Speak to the microphone.
Very different because you don't have a spin-on bundle.
Yeah,
It just look like a double operator into that.
Yeah.
So it's very, very far away from all.
But I
spectral triple.
maybe like when I specialize on SU2Q, like finding a very concrete representations of this, maybe they are could be agree. I guess I don't know. I think
It's different. This is a different construction. You construct basically the Cauchy-Riemann operator and takes its adjoint.
yes.
Whereas this is not it's not the spin bundle. It's not the Dirac operator on the spin bundle.
Yes. I mean in the case of non-commutative tutors, this is modeled on this double Laplacian. Yes, indeed, yes. But yes, for this spectral triples on the quantum SU2Q, but I don't know.
I thought that these were close to the spin bundle.
Yeah, but yes, but I mean, at the beginning, it looks like from a complete different ideas, but after specialized doing some concrete computations, it might be.
No. You start with the functions. Your operator starts with a function and maps in a different Hilbert space. The Dirac operator has a spin bundle. Okay, it's trivial.
Yeah.
But it maps two copies in two copies.
Yeah.
So this cannot be the same.
But there are still two copies, like H0, H1. But
yeah, but you start with one and then maps. No, I don't think that you have one forms.
Yeah.
You have functions.
Yeah, you are both right.
But
But you are talking about the Dirac. You are talking about the Dolbeau operator.
that's what he
Okay.
constructs.
So this means that this is an analog of a complex structure.
But
Only in dimension 2, complex structure and conformal structure, they coincide. But in higher dimensions, these two ideas diverge.
yeah.
exactly.
I mean, probably even on non-commutative tutor, the construction like have slightly different. But I was talking about this quantum SU2Q.
Yeah, but it has is a three-dimensional manifold. You don't have complex structures.
But
I
what would be?
I don't need. Right?
But there's a problem. There's a problem for SUQ2. Okay, classically speaking, it is something like three-dimensional manifold. It cannot have a complex structure.
No, but
So maybe you could consider this H1 related somehow to contact structure which exists on three-dimensional sphere. But then you don't obtain elliptic operators. Then you obtain hypoelliptic operators, like in theory of Earp and Baum and Earp. Okay. So it's hard to say what kind of curvature you are obtaining from your construction, even classically, because usually curvature, every kind of curvature is an infinitesimal obstruction to making some structure flat. Okay, it's not clear in your general case what is this structure you are computing the obstruction of being flat. Okay, so it's very hard to interpret what kind of curvature it is this.
Then yes, that's why I'm thinking I will give up to prove something flat. I will just find some applications in this probability setting. It's I mean, flatness, I don't know. It's because it's about shape, right? So it's in the quantum setting, it's
yeah, but there are so many shapes in differential geometry. Something could be modeled on a flat space. Something could be modeled on a homogeneous space. Okay,
Mhm.
or maybe on some nilpotent group, yeah, like in the
Mhm.
case of contact geometry when you are playing with this Heisenberg group. So these model shapes are various, and with every such a shape, there is a infinitesimal abstraction for flattening this model, this manifold, to make it
Mhm.
locally isomorphic to this rigid model.
Mhm.
Okay, but in this very general language, it's hard to say what kind of geometry are you going to flatten
Yes,
by your
indeed.
curvature.
So I think we are only at the stage of fighting with examples and then to see, yeah, what's the.
I have a question. If you could come back to this H and K and this functional equation. Okay, I ask you whether this could be interpreted as the fact that H is a co-boundary of K in some complex.
Yeah.
Okay.
Yeah.
Now I'm wondering, okay, what are you considering above, which is underlined in red?
Yeah.
This is some variational problem.
Exactly.
And with every variational problem, you have associated variational complex, classically, at least classically.
Mhm, mhm,
Okay.
mhm. Yeah.
So it means, so it rings me a bell. Okay.
Mhm.
Because maybe there is some, maybe this kind of relation between H and K comes from the classical variational problem.
Mhm.
Okay.
Mhm.
And the fact that you can apply it to these operators like this nabla
Yeah.
with the slash,
Mm.
everything depends on the fact that these two nablas are applied to different tensor factors. Therefore, they commute. So everything reduces
Yeah.
to a function of
Yeah.
two commuting variables and so on and so forth. But I'm not familiar with this equation. I saw similar equations in this theory.
Yeah.
In Tretkov and there are many places. Yeah, but now I see that maybe there's a source of this functional equation coming from the variational problem of varying metric in a given conformal class.
I have the complex, but I have almost the ingredients of the cyclic structure. I mean, the only thing fails is that in my complex, you see the simplicial structure and the co-simplicial structure do not compatible. That's that's what I have so far. Indeed, there is a complex like a the consider functions of like a different one variable, 2 and 3. So you have this complex, and then you have some phase map and degeneracy map and the cyclic map. But I think the only axioms that different from the cyclic theory is the compatibility between the simplicial and the co-simplicial part. So yeah, probably then I have to look for new like a algebraic tool to understand this.
In the variational complex, this cyclic symmetry comes from integration by parts. So
exactly. So this exactly.
So for me, it's this variational approach looking through this, behind this.
Yes. So yes, indeed. This integration by part is encoded in the cyclical in the framework of cyclic cohomology. It's like there is a compatibility between the simplicial structure and the co-simplicial structure and the cyclic structure. Right? So that's basically the integration by parts. So yes, I use it a lot to simplify computation. Indeed. Yes.
Do you have an analog of your equation in your more general second part of your talk? Because
Yes.
I missed it.
So you mean
did you say anything about this?
You mean this
something like such conditions?
Yes, this if you go high dimensional like examples, so it holds. Yes, it holds. When with the
same.
Yeah, with slightly modification. Yes, the same structure holds. Yeah. Yes, indeed. Yeah.
Okay. Thank you.
So last words, I think that in this last example of probability, there is no demand of complex structure, right? I'm just there are some two Hilbert, like two parts of Hilbert space, like I can construct D, and that's also, I think that's sufficient to set up a sort of a problem in Riemannian geometry in a previous sense. Like you can, if you can sort of prove the zeta function exists, right? So then we are in a good business.
Could you check?
Oh yes,
Yeah,
I see.
yeah, there are people on Zoom, so maybe Anna would like to comment. Hello, Anna.
Hello. Well, it was very nice to hear your talk.
Thank you.
Can you hear me? I hope
Yeah,
my
yeah.
Yeah, we can
connection
hear you. Yes.
is good enough. Maybe I just remark something that is written on this slide exactly, but was not emphasized, that our construction works only for symmetric
Oh yeah.
operators. So,
Yes, exactly.
since you have been discussing about this complexification problem, maybe this implies some kind of reality condition. I don't know. I have no no feeling about it, but that was an important point in our construction.
Yeah.
Otherwise, it doesn't work.
Yeah. Because this symmetric, it means that we want our Laplacian is usually symmetric, right? Yeah. So that's why we put this symmetric condition. So we have to, because this L of phi is exactly playing the role of Laplacian operator, so it has to be symmetric. I mean, yes, I mean in Anna's paper they propose like two. One is GNF symmetric, which means it's symmetric in this sense, and then they propose some KMS symmetric. It's sort of a twisted symmetric. I guess in that case we can construct some twisted spectral tree. So that's my speculation. So
that might be interesting. I think we tried and we failed to construct spectral triple in that like more general symmetric case. But yeah, well, we just didn't find the proper way to do it, but it still can be possible, of course.
I see. That's my hunch. I have not get time to do the concrete computation.
Oh, come on, you had 24 hours.
Okay, no more questions or comments. Let's thank the speaker. So this closes our session.
Thanks again for the nice talk.
Thank you.